Part A asks us to propose 3 structures which are compatible with this spectrum and with that molecular formula. And it says you've got to explain your reasoning clearly. What that really means is that you've got to identify the key peaks in the infrared and justify the way you've assigned them by quoting the datasheet. Okay, a lot of people didn't actually quote the datasheet, and they won't necessarily then accept what you've said unless you've done that. So the important thing then is to look at this and, for example, see this strong peak around 1700 and say, right, that looks to me like a carbonyl peak. But it's not enough to say, oh, there's a strong peak around 1700, that's carbonyl. You've got to show that it really does fit. And the way to do that, as we've said before, if you've watched some of the videos I've done, is to say, right, it tells you in the datasheet that 1630 to 1820 is the range for a carbonyl peak. So you get your sort of set square or whatever you're using as a set square like this, and you move it to 1630, which might be, you know, somewhere here, and you say, right, that's the one edge of the peak. 1820, you again do the same thing and draw a line at around 1820, and you know, you get something like this, and you can see then that that really does fit in that window. So you can say this is C double bond O, but you must quote those numbers from the datasheet when you're doing that. Okay, so you say the structure clearly contains a C double bond O group as shown by the peak at 1630 to 1820. Now when you come to this end, these sharp peaks, remember, around 3000 are CHs. You can mention them if you want, but you're not expected to, because they don't really give you any clues as to what the structure is, and there wouldn't be any marks for that. The one that's important at this end is this one. Now the crucial thing is that that's an OH peak, but that there are 2 different types of OH peak. If you look on your data sheet, you can see it distinguishes between alcohol OHs and carboxylic acid OHs. The peaks look very different, and therefore you can tell what kind of OH it is. Now a lot of people ignored that, and they just said it's an OH, so it could be a carboxylic acid, it could be an alcohol. There should never be that kind of ambiguity if you've got the infrared spectra, because the peaks look very different. So when you see one like this that's clearly shifted to the high wave number side of the CH peaks, that looks like an alcohol OH peak. We'll talk about what the carboxylic acid one would look like in a minute, but that looks like an alcohol peak, and you need really to learn to recognize that. But again, you can't just say it looks like an alcohol peak. You have to go to your data sheet and look up where an alcohol peak should be, and it tells you 3200 to 3600 wave numbers. So again, you mark that on and you say, right, 3200, that looks like it's about here. 3600, you know, that looks like it's about there. And so you draw your lines down, and again you can see that does indeed encompass that peak. So you can say that's an alcohol OH, not just OH. Okay, that's an alcohol OH bond. And again, quote the datasheet to justify why you're assigning it as that. So you have to get those 2 things. Let's just pause and think about what it would have looked like if it had been a carboxylic acid, because it's really important to learn to recognize those. You can see some actual carboxylic acid spectra in question 2, just again to get used to what they look like. But the important thing is that the range for those, the carboxylic acid OH, is 2500 to 3300 wave numbers. You can see that's very broad. You know, where here we're talking about a width of about 400 wave numbers, here we're talking double that, so it's a much broader peak. And that means that 2500 is here, and you shouldn't have reached the bottom of the peak there. 3300 is sort of here, and again you shouldn't have reached the bottom of the peak there. So what it's going to look like is sort of something like this, encompassing the CHs. Usually it has a sort of slightly funny shape kind of like that. Okay, that's a carboxylic acid OH. It's very different looking. But the crucial thing is, if you drew these lines down at 3,200 to 3,600, you'd say, oh, no way does that peak come within there. So it's very clearly not an alcohol OH, it's a carboxylic acid OH. And that means when you come to proposing structures, it can't be a carboxylic acid, it can't have that COOH group. So you've got to have a carbonyl group, and you've got to have an OH. But they must be separate from each other. The OH can't be attached to that carbon. Okay, so now we have to propose 3 structures, all of which have that molecular formula, and each of which contains one of those, and separately one of those. When it says write down the structures, you can use any format that you like, but I really strongly urge you to use skeletal formulae. Some people are still using displayed formulae, and the problem is that there's no difficulty with them. You know, you're not going to lose marks or whatever for using them, but it just takes so long, and as molecules become more complicated, they become much more difficult to draw in an intelligible way. So please do try to get to grips with skeletal formulae, because they will make your life so much easier in the end, and in a lot of the stuff in the second year you really have no choice, but so now would be a good time to do that. So if we've got 3 carbons, we know that they're all going to have to be based on that. Okay, so that's 3 carbons in a chain. And if we think about where the carbonyl group can go, you can see that it could go at the end, or it could go in the middle. So that gives you your starting point, that group's got to come from one of the carbons. That end or that end, well, you know, it's the same. So let's say it either goes at the end or it goes in the middle. And then we've got to put the OH group on as well. Not here. That would be a carboxylic acid, and we've ruled that out. So that is not a permissible suggestion. But it could be here. So we'd have the 2-hydroxy isomer, or it could be here, which would be the 3-hydroxy isomer. Okay, so those are the 2 possibilities if we have the carbonyl group at the end, which remember is an aldehyde group. So 2 possible aldehydes, or we can have the ketone, which is this one, and you can see that if we put the OH either here or here, it's the same thing, because if you just flip it over, the OH would move from there to there, it would be the same thing. So there's just one possible ketone, which is that. The other thing that's worth mentioning, because again a few people slipped up on this, is you've got to be very careful. You can't write OH like that. Okay, the bond has got to clearly attach to the oxygen, not to the hydrogen, because that's the way it's actually connected up. So here, that's why I've drawn the OH there, so the bond clearly connects to the oxygen, and here it's got to be like that to get the structures correct. So those are your 3 candidates. You can check they really do have that molecular formula, you know, that there aren't any other double bonds or anything, because we've got 3 hydrogens there, 1 here to account for the 4 bonds, so 3 plus 1 is 4, plus 1 is 5, plus 1 is 6, so that's correct. Part B then shifts attention to the mass spectrum, which looks kind of like this, and it asks first of all about this peak with an M over Z of 74. So the important thing is to give it its name, which is the molecular iron peak. Okay, which means that, and you can explain it if you want, although that would really be enough, but you need to know at least that that means that it comes from the intact molecule. It hasn't lost any atoms, you know, minus 1 electron to turn it into a positive ion. That's what the molecular ion is. But you didn't need to explain that there. What you did need to do was to explain that it's the molecular ion peak, and then it says what's the significance of it. So that may not be enough, because that's what it's called, but the significance of it is that M over Z, which is 74, is equal to the MR for this peak. Okay, that's the significance. But again, be careful with your words. Don't say things like, people said things like, this peak is the MR. I mean, this peak isn't the MR. This peak is the molecular ion peak, but the significance of it is that its M over Z value equals the MR. So make sure you really say things precisely and not just kind of vaguely. So that's a really useful peak. Remember that little peak at 75 comes from the fact that a small proportion of the molecules contain one carbon-13 instead of a carbon-12, which gives you the one extra mass. I didn't ask you about that here, but make sure you don't get confused when you're looking for molecular ion peaks. It's the peak with the biggest M over Z value, in other words, the one furthest to the right, except for that little satellite that it always has. C now then asks us about fragment ions, which can often let you distinguish between possibilities, and that's really what it's getting you to do here. So fragment ions result, remember, from the fact that when you ionize the molecule to create the molecular ion, you generally do that by firing very high energy particles, like high energy electrons at it, and they hit it very hard in order to knock an electron out of its place. But in doing that, they generally give it a lot of kinetic energy, so it shakes very violently and it can break up into bits. And the crucial idea is that different fragmentation processes are possible, so not all the molecules will do the same thing. It's something that's difficult to get used to, because you kind of, in chemistry grow up with the idea, when you add this to this, this happens. But with fragmentation of ions, it tends to be more unpredictable than that. Sometimes one bond will break, so there'll be a peak that comes from a population of molecular ions where one particular bond broke. But in another population of ions, it'll be a different bond that breaks, so you'll get different fragments. And you'll see them both in the spectrum, because the spectrum comes from many, many ions, not just one. Okay, so the peak that you see in the spectrum will be the result of, thousands of trillions of ions being created, some of which will have been created by one fragmentation process, some by another one. Okay, so let's see how we can identify which of these structures can give us the two most prominent peaks. Okay, these ones that they picked were the ones with the biggest intensity. That means that they're the best populated fragments, the fragmentations that occur most frequently. And those generally are the only ones you can interpret. The little tiny peaks down at the bottom, don't even go there, because all kinds of things can happen to cause those in the spectrum. So if we start with this one, we can just go through and think, right, how might it fragment, and what would be the masses of the fragment ions you would get? So the only types of bonds that are likely to break commonly, and therefore give you an intense peak, are single bonds. So don't even think about the double bond breaking, because that's very unlikely to happen. Obviously single bonds to hydrogen might break, but that would just take one off the mass, so those are not interesting. What we're looking at in this molecule really is this bond or this one. Those are the only two single bonds that will give you fragments of any interest. And that's the point, that it's not like there are hundreds of possibilities, and how on earth are you supposed to know? In the examples you get at A-level, there will always only be very few possibilities. And so you can just go through and say, right, if it broke here, what would you get? Well, on this side, you've just got CH3. So the fragment ion you would get, if it broke there, would be CH3+. On the other hand, when it fragments, you never know which side the positive charge is going to go. Sometimes it goes one way, sometimes it goes the other, sometimes it's unpredictable, and you would see both possibilities in the spectrum. Again, just consider all of the possibilities. Don't worry about which is more likely to happen. So if it broke there, you would have CHOH, CHO. Okay, so CHOH, CHO, and the whole thing would have a positive charge. Easiest thing to do is put a bracket around it and put the charge outside. And you could either add up that lot to get the mass of that peak, or you could realise that the total MR is 74, as we know, and it's just lost 15 there. And that gives you 59. So if it were that fragment, it would give you a peak at 59. So we've got an M over Z of 15 as a candidate here, and an M over Z of 59. So 59 we're not interested in, it's not a particularly prominent peak in the spectrum, but 15 is. So far that's looking good, because we can account for the peak at M over Z of 15, but so far we haven't accounted for the peak at 43. And for our structure to be viable, we have to account for both of them. So let's then look at what happens if it breaks here instead. Remember, it's not about breaking as well. It's only ever going to break once in one molecule, or at least if it's a prominent peak, that's all that could have happened. So it's not breaking there as well as here. This is what if it breaks there instead. So again, we can write down what the structures of the fragments you'd get would be. So here we'd have CH3, CHOH. So CH3, CHOH, and remember always in mass spec must be positive ions. So it's CH3, CHOH plus. Or if it breaks there, it's just CHO plus. And if you add the masses of those up, you get 15, 28, 29, 39, 45 for that one. And for this one, we get 16, 28, 29. Okay, so those are fragment ions which could be formed if this were the structure, but neither of them has an M over Z of 43. Don't say, oh, 45 is pretty close. It's got to be absolutely on the nail, otherwise it's not a plausible fragment. So the problem with that is that we can't account for M over Z is 43. So that means that this is unlikely to be correct. Okay, now that seems possibly like quite a lot of work, but if you practice, it's actually very quick to do this, because you know what you're doing. You're just identifying the bonds that can break and just quickly adding what's the mass up on that side, what's the mass on that side. And if they don't fit, it's not a plausible structure. So let's do it for the other two. Okay, so for this one, again, there are two places it could possibly break to give us meaningful fragments. Well, three, I guess, because you could take the OH off here. But if you took the OH off there, that would give you 17, which we're not interested in. And so I guess we should include that as a candidate. And rather than work out all the fragments this time, you can probably see straight away that we're not going to be able to get 15 from that. Because, as I say, if you break the OH off, that's 17, that's too much. At the other end, we would have to break this whole CHO off, which is 29. So there's nowhere, actually, that you can just break 15 off the end. So we can straight away rule that one out without working out all the details by just seeing that M over Z of 15 cannot easily be created. So again, it's unlikely to be this. So you could go through and work out all the possible fragment ions from that, but it's quicker just to spot there's no way it's going to be right, because you can't get 15 from that one. So we have to hope it's this one, because that's the only one left in the game. Okay, so two possible candidate bonds to break. Again, we're not interested in this one because we know that would break 17 off the end, which is no good to us. So really it's a question of this one being a possible breakage site, or, not and, but or, this one being a possible breakage site. So what happens if it breaks here? Well, again, you can see this is looking good because that breaks CH3 off the end, which would give us CH3 plus. And of course that adds up to 15. So that would account for the M over Z of 15. So that's good. The other fragment is too big, because we'd have COCH2 OH. Okay, so COCH2OH plus, but that's going to give you an M over Z of 59. So we're not interested in that one because that's not a well populated peak. But what about here? Well, again, two possible ions that we could form depending which side the positive charge ends up on. If it ends up on this side, we get CH2OH plus, and if it ends up on this side, we get COCH3 plus. So if we add up the M over Z for those ones, we've got 14 plus 16 is 30 plus 1 is M over Z is 31 for that one. Here we've got 12 plus 16 is 28, 38, 40, 43. And finally, you can see we've struck the jackpot with that one, because 43 is what we've been looking for, and we got it right at the end there. So if that bond breaks and the positive charge ends up on this side, on this side, so if this bond breaks, we get the positive charge on this side, we get COCH3 plus, and that would give us the M over Z of 43. So you can see this molecule, if it forms a molecular ion and that then fragments, we could get this ion or that one, and that's what we see as the most populated ones in the spectrum. So this can give both well populated fragment ions, which means that it's the likely structure out of these three. I mean, it doesn't prove that it is the structure if you had no other information, but since we'd already narrowed it down to those three, and it definitely wasn't the other two, it's basically got to be this one. Part D asks us to give a name to this compound. This was a mean question because we haven't probably come across this issue before, but it's a good place to learn it anyway. The problem is that that group is a ketone. Okay, when you have C double bond O with carbons on both sides of it, that's a ketone group, and that means that we would normally have the ending -one. And this group is an alcohol group, and that means we would normally have the ending -ol. And the trouble is you can't have them both as the endings. The only time you can do that is when you have an alkene and an alcohol or something like that. You can call it an -ene-ol. So this, for example, would be but-2-ene-1-ol. Okay, because the alkene starts at 2 and the alcohol's on 1, so that would be but-2-ene-1-ol. But otherwise, these other endings, -one and -al and -ol and oic acid, you've got to choose one of them to be your ending. And the other group is therefore going to have to be named in a different way that doesn't make it an ending of the name. So what you do is to think, well, is there a different way to name this group or this group? And the answer is actually yes for both, but this one you don't learn at A-level, this one you do though. When you have an OH group in the structure and it's not possible to use ol because you need a different ending there, you can call it a hydroxy group. So the way you name this is to say, right, if it didn't have the OH and you just had that, that would be propanone, but we need numbers in this case, so it's propan-2-one. Okay, we've got 1, 2, 3, so the ketone is on 2. Propan-2-one, and the OH is on carbon 1, so it's just 1 hydroxy propan-2-one. Okay, 1 hydroxy propan-2-one describes that structure. It's got to be hydroxy, not hydroxyl with an L. That's a term that biologists use, but I'm afraid it's not approved of in chemical names, and not hydroxide either. So that's the answer.